We're going to make a little table here. The table is going to look like this. We've got elastic, and we've got inelastic collisions listed along the vertical axis there. And along the horizontal axis, we're going to put kinetic energy, and we're going to put momentum. We're going to put little check marks and X's here to refresh our memory on which ones are conserved and which ones aren't conserved in each of these types of collisions. If we have an elastic collision is one in which kinetic energy is conserved. Yes, so we'll put a little check mark there. What about momentum in an elastic collision? Yes, momentum is conserved, of course, in an elastic collision. Momentum is always conserved, right? As long as it's an isolated system. What about in an inelastic collision? What about kinetic energy? No, it's not conserved. In fact, if it's not conserved, what are we going to notice about it? It's going to be greater or less. It's going to be less than what we start with. What happens if it's greater than what you started with? You made a mistake, so try it again. Okay, make sure you get a number that's either the same as what you started with or lower than what you started with. What about momentum in an inelastic collision? It's conserved, yeah. So momentum is always conserved. Kinetic energy is sometimes conserved. Now, there are certain types of collisions we can just read the question and determine right away whether it's elastic or inelastic without doing any calculations. What kind of question is that? What scenario are we going to see that tells us right away this is either elastic or this is inelastic without the need to do calculations? Yep. Yeah, if they bounce apart, we don't know whether it's elastic or inelastic. In all likelihood, it's inelastic. But if they stick together, we know for sure that it's inelastic. If they don't stick together, and if we do need to do a calculation to determine whether it's elastic or inelastic, what calculation is it? What calculation do we have to do? It's not PI equals PF, right? Okay, that's certainly a valid thing to do when you have a collision, but it's not going to tell us whether it's elastic or inelastic, Chad? Yeah, calculate the initial and the final kinetic energy. Now, we pointed out a couple of things yesterday with this. 1/2 m1 v1I squared plus 1/2 m2 v2I squared. This assumes there's two objects before the collision. If there was 14 objects before the collision, then we'd have 14 of those terms, right? Instead of just two of them. We're going to calculate that initial kinetic energy. We cannot cancel out m's, as some people did yesterday. Even if it's the same mass, why can't we cancel it out? It's not on both sides. It's got to be in every term, not just every term on the right-hand side, but every term on the left-hand side and the right-hand side. So don't cancel out masses, even if they're the same. Now, if you've got a collision where you're using conservation of momentum and the mass is the same, you can cancel it out because it appears on both sides, right? It appears on the left, the initial side and the final side. If in doubt, don't cancel, because you can always get away with the not canceling, right? The other thing was direction. Let's say V1I was 10 and V2I was negative 12. What would we plug in there for V1I? 10, right? 10 squared. What would we plug in for V2I? 12, right? We wouldn't put in the negative because although for momentum's a vector, we would put in the negative. For kinetic energy, we got a scalar there, so we're not going to pay any attention to direction. Even if V2I is 16 meters per second at 24 degrees north of west, we would still put in 16 meters per second and not the angle, not the direction, because again, kinetic energy is a scalar. So we get that initial kinetic energy. We do the same thing for the final. And once again, if they're the same, we know it's elastic, and if it's kinetic energy lost, we know it's inelastic. If it's more than what we started with, we know we made a mistake, and we should check our work. Good? There are two questions on tomorrow's quiz. These are basically those two questions. Now, the context of this first one can be anything, right? Okay, we did a question yesterday, I think it was a multiple choice question, where we had to identify kinetic energy being lost or kinetic energy staying the same, momentum staying the same, so on. Okay, you're going to see something like that, maybe in a completely different context, doesn't matter. Okay, it's going to require you to know that momentum is conserved all the time and kinetic energy is only conserved in an inelastic collision. Got it? Second question on that quiz is going to be something like this. Determine whether it's elastic or not. Get the initial, get the final, don't pay attention to directions. If it's the same mass, don't cancel it. Okay, if it's the same kinetic energy, it's elastic. If it's less, then it's inelastic. Get it? Okay, you understand that? You got 100% on tomorrow's quiz. Yesterday, we took a look at collisions that occur in 2 dimensions. And we started off the lesson yesterday on the 2-dimensional collisions by taking a look at individual 1-dimensional collisions. The first one we looked at something like this. Car number 1 or object number 1 moving at, say, a speed of 10 meters per second, doesn't matter what speed it is, going towards object number 2 that's at rest. Then we had object number 1 at rest and object number 2 coming towards object number 1. Maybe it was at 15 meters per second. It doesn't really matter. We know when we see problem number 1 here, we'll call this one number 1 and this one number 2. We know that when we see problem number 1, it's a pretty straightforward question. We just say always Pi is equal to Pf. M1 V1I plus M2 V2I equals, I'm writing down MVF. What do you know about this collision to be true if I'm saying the final momentum is MVF? Tristan? They stick together. If they didn't stick together, I would have made it M1 V1F plus M2 V2F, right? So these guys stick together. M1, don't know what it is, but if this was a real question, we would. V1I is 10 meters per second. M2, again, we'd know it if it was a real question. V2I is what? It's right in front of us, literally staring us in the face. V2I is 0. Yeah, so we're going to cross that off. And then, of course, M is the combined mass. VF is likely what we'd be solving for there. We do the same thing over here, but this time it's along the y-axis. Looking at it from above, we would say Pi is equal to Pf. M1 V1I plus M2 V2I equals, again, let's assume they stick together, MVF. This time, this one is 0 because object number 1 isn't moving. We're going to end up solving for VF here. So we've solved this question, question number 1, a million times before. We've solved question number 2 a million times before. You guys have been quizzed on this a couple of times, and you've done very well on it. So we shouldn't be struggling to a huge degree at this point on the questions that we've got up on the board here right now. But what if we change it? What if we change this question to look something like this? What if we put car number 1 or object number 1 going to the right at 10 meters per second and object number 2 going upwards at 15 meters per second? They collide at this point right here. They go off as one. They stick together. They go off as one. Somewhere up here. How do we know, by the way, it's going to go up here, the wreckage? How do we know it's going to go up and to the right? Braden? How do we, go ahead.
Because they're both heading a little up, right, I guess.
Okay. In the end, we know that momentum is conserved in both dimensions, right? If we have momentum to the right before the collision, we have to have momentum to the right after the collision. If we have momentum up before, then we have to have momentum up after. If there's only one object afterwards, it's got to have momentum to the right and up. Whereabouts up there, we don't know. That's okay. We're just making an educated guess that it's going to be up there somewhere. We're going to cover up those initial diagrams that we drew up here, those one-dimensional problems. Now we're going to go back to looking at this question that you see down here. We're going to call it question number 3. For question number 3, what we want to do is ignore either this or this. When we're dealing with the x component, we should ignore this. When we do, we get exactly the same thing as we got for problem number 1. Basically, if we ignore object number 2 we assume that it's at rest. We pretend it doesn't exist, it's at rest. It's not moving, it doesn't have any momentum. So we're going to say m1 times 10 is equal to plus 0, because object number 2 doesn't have any momentum in the x direction, equals mvf, exactly the same as it was for problem number 1. Well, then we're going to ignore object number 1, because we're looking at the y component now. So ignore object number 1. Same as it was for problem number 2 up here, where object number 1 doesn't have any velocity, so therefore no momentum. Object number 2 is moving up at 15. Solve for VF. This time, though, once we have VF, Emily, for the x component and the y component, what are we going to do with it? We were done when we did problem number 1 and problem number 2, but with problem number 3, we get these two values. We're not done. What do we do with them? This is your physics 30 problem. This is your physics 30 problem. Now it's time for your physics 20 problem, which says, yeah, you need a vector diagram. Look, we've got momentum to the right. Okay, that's the x component. We have a momentum upwards. That's the y component. We're going to find the hypotenuse here using the Pythagorean theorem, and we're going to find the angle at the start of the diagram by using the tan function. Make sense? Now, we did example 9.13 yesterday, correct? Okay. You guys comfortable with that? Let's give these two questions then a try on page 492 and see what you can do with them, okay? Put up your hands, call me over, okay? Do what you got to do to understand this, okay? Show your work. Draw the picture. Show your work. Put arrows on the diagrams. Okay? Show x and y components. Show your equations. Don't just skip steps. Because when you make a mistake, it's a lot harder to find those mistakes. Okay, let's see what we can do, and then we'll take a look at them in a few minutes if we have to. Let's take a look at another sample question. This one is real similar to what we did in the sense that it's a two-dimensional interaction where we have momentum being conserved, but this one's an explosion as opposed to a collision. We have a 0.6 kilogram fireworks bundle at rest just before it explodes into 3 pieces. You got a 0.2 kilogram piece going to the west, one that's 0.18 kilograms going to the south, and we're going to find the third piece after the explosion. Here's my explosion point. We have a piece that goes to the west. We're going to call that piece 1. I don't want to call it piece A because I don't like letters, I like numbers. But in the end, if you want to call it piece A, go ahead. Piece 1 or piece A has a velocity of 14.6 meters per second, along with a mass of 0.20 kilograms. Now, piece 2 or piece B, whatever you want to call it, is going to the south. So we're going to draw it going this way to the south. Object number 2, 19.2 meters per second with a mass of 0.18 kilograms. There's a third piece, though. Where does the third piece go? They don't tell me. Anybody want to take a stab at where the third piece is going to go? A lot of you may be able to determine this just intuitively, right, without even really giving it some thought. But what's the answer to the question? Kidding? Down this way? No. It's not going to go this way, but you're not all that far off. Tristan? It's going to go opposite to that. It's going to go up this way. Now, Tristan, how did you know that it goes opposite to that? No, it didn't really make sense. Your answer was right. Your explanation was suspect.
Because they're both moving in like relatively different directions, like opposite.
Yeah. Yeah, you can look at it in two ways. You mentioned the word force, Newton's third law, which, by the way, Newton's third law comes directly from the law of conservation of momentum. Basically, it says that there's a force on object number 1 one way, there's got to be a force on object number 2 the other way. So if object number 1 goes to the left, then the other object is going to go to the right. If object number 2 goes down, then the other object is going to go up. If we look at it in terms of momentum, however, the total initial momentum of this system is 0. The total final momentum is also 0. If we have a momentum to the left of whatever value, 0.2 times 14.6, that would give me, 2.92 kilograms meters per second for the momentum to the left. Well, there must be 2.92 to the right to balance that. And if there's, whatever this is, 19.2 times 0.18 downwards, then there's got to be that same amount upwards. So we have to have momentum to the right, and we have to have momentum upwards. Now, what's the exact angle? Is it exactly northeast, as somebody suggested? Probably not, although it could be, coincidentally. Okay, we don't know exactly where it is. We just know ballpark where it is. Okay, let's do our thing here with the x's and y's. We're going to say pi is equal to pf, as we do for every conservation of momentum problem. This time, the initial momentum is what? As this object is at rest before it explodes, its initial momentum is 0. The final momentum this time is due to 3 objects. I think this is the first question we've had this year where there's been more than 2 objects in one side. But it doesn't need to mess things up. It doesn't need to confuse us. We just have an extra term, that's all. M1, remember, as we're doing the x components, we're ignoring something that's on the y-axis. So we're ignoring object number 2. For us right now, object number 2 is dead. It doesn't exist for us right now. Object number 1 is the only one that really matters initially. Object number 1 has a mass of 0.2. It has a velocity of what? What's V1F? I was ready for somebody to give me the wrong answer there. Negative 14.6. Good. This is 0 because V2F is only on the y-axis. M3, oh, we don't know M3, or do we? If it's 0.6 total, and object A has 0.18 and object B has 0.2, then we're going to subtract those two numbers from 0.6. We're going to get 0.22, I think it is, isn't it? Yeah. 0.22 kilograms. And we solve for V3F. Now, let's calculate this on our calculators here. If we say 0.2 times 14.6, take it to the left side by adding, because it's a negative on the right side. Divide that by 0.22. We get 13.2727. Are we done? Not at all. What have we just found? The x component of the third object. In other words, we found the green line there. So now we do the same thing for the y component, where once again we'll say pi is equal to pf. M1 V1I plus M2, what's the initial momentum? 0. It's all at rest. Equals M1 V1F plus M2 V2F plus M3 V3F. 3 objects, 3 terms. Which one do we want to pay no attention to this time? Which one has no velocity as far as we're concerned right now for the y-axis? Number 1, it's moving, but it's moving on the x-axis, so it's irrelevant to us for the y-axis. M2 is 0.18 kilograms, and V2F is what? Negative 19.2. M3 was, what did we say it was, 0.22 times V3F. Solve for V3F again. I'm going to say 0.18 times 19.2. We're taking it to the left side by adding, and then we're going to divide that by 0.22. 15.7091. Okay, so what's next? Each of these problems is like 3 and 1. there is the x, there is the y, and then there's the combining of them, which is physics 20 vector problem. What's next? Draw the picture, draw the vector diagram. This is what we call a situational diagram, just shows what's going on. The vector diagram must be drawn head to tail. So we've got one that's 13.2727, then we've got the next one that's drawn head to tail, 15.7091. Let's get the speed there by doing the Pythagorean theorem and the angle as measured from the beginning by doing the inverse tan function. What do we get for the speed there? What is it? 20.56. We're going to round that to 21, I think. And of course, we want to find our angle. We're going to find our angle by using the inverse tan function of opposite over adjacent, 15.7091 divided by 13.2727. Make sure you're in degree mode. Okay, on your calculators, after they get cleared on your unit test, click sine 90. What should it equal? If you're in degree mode, it should be 1. If it isn't 1, then make sure you go into degree mode. Okay, so let's find the angle here. We got the inverse tan of 15 over 13. 15.7091 divided by 13.27. We get 49.8 degrees. Is that good? 49.8 degrees what? We have to express this as a north, south, east, west frame of reference now because that's what the question did. This would be 49.8 degrees north of east. Let's give our practice problems that go with this one a try, please, on page 495. If you haven't finished the ones on the last page, work on them and get them finished. If you have, then move forward to this one, page 495. Okay, let's take a peek at number 1 then. Number 2 we'll go over in due time, but we'll hold off on that one for now. It says a 0.058 kilogram firecracker that's at rest explodes into 3 fragments. One goes north, one goes east. Where's the third one go? Let's draw a picture. This is our explosion point. We have a point 0, we'll call this object number 1, 0.018 kilograms going directly north at 2.4 meters per second. We have another one going east. We're going to call that object number 2. It has a mass of 0.021 kilograms, and it has a velocity of 1.60 meters per second. Now, the third piece, we don't know exactly where that's going to go, but we can make a pretty good prediction. Where do you think that it's going to go? It's going to go down and to the left, right? If we have a momentum that's up, we have to have a momentum that's down. If we have one that's to the right, then we have to have one that's to the left in order to balance that. So it's going to go down here somewhere. Do we know what its mass is? Not right away, we don't. But we can do a little subtraction in our heads here. 0.058 subtract 0.018 subtract 0.021 is going to give me, I think, 0.019. Is that right? Okay, and of course we want to find its speed and direction there. So we break it up into x and y components. Here's our x. We're going to say pi is equal to pf. And we're going to say that the initial momentum is 0 because the whole thing is at rest. Afterwards, again, just like the last example we did, m1 v1f plus m2 v2f plus m3 v3f. Masses cancel here. They don't cancel. But if they were the same, would they cancel? Yes. Even though the mass doesn't appear on the left-hand side, we could cancel it because in the end, you divide everything by that mass, right? And if you divide 0 by that mass, it would still disappear. So if they were the same mass, you could cancel. In this case, we don't, though. Object number 1, how much of that 2.4 meters per second is on the x-axis? We're ignoring everything on the y-axis right now and paying attention only to the x. How much of that 2.4 is on the x-axis? One word. None. It's all on the y-axis. None of it's on the x-axis. M2 is 0.021, and V2F is 1.6. All of that 1.6 is on the x-axis. We solve for V3F there. Let's grab the calculator and give this a try. 0.021 times 1.6. Let's take that to the other side by subtracting. Let's do it properly, though. We get negative 0.0336 when we take it to the left side by subtracting. And then we divide that by 0.019. And we get 1.768 to the left. What have I just found? It's not my final answer. What have I just found? What does this mean, this 1.768? Yeah, it's this, right? It's the x component of the velocity of the third object. Okay, that's part of what I want, but not all of it. So I've got to do a little bit more work here. Let's go to the y components. Once again, we're going to say pi equals pf. Pi is 0 again. Pf is m1 v1f plus m2 v2f plus m3 v3f. 0 is equal to, what do we got here? We're dealing with the y's only and not the x's. How much of that 2.4 is y component? All of it. How much of this 1.6 is y component? None. So we're going to scratch off m2 v2f. m1 was 0.018 times 2.4, I think it was. Yeah, times 2.40 meters per second. Plus m3 times v3f. Let's solve for v3f now. Okay, let's take it to the other side by subtracting. And let's divide that by 0.019. 2.27. That's going to be negative. Now let's combine them. 1.768 to the left. We can drop the negative now. Why is it okay to not put a negative in for this x component of the velocity now? We have to show direction some way. We've already done that with our picture here. We're drawing it to the left. That shows direction. Okay, this one is 2.2736. We can also drop the direction here. We'll drop the sign there because we already have direction indicated by the arrow. Let's do the Pythagorean theorem to get v. We should end up with 2.9 meters per second. Let's do the inverse tan function to find theta. Theta should work out to be 52 degrees. So what's our answer? 2.9 meters per second, 52 degrees south of west. Is that good? Okay. If you can get number 2 tonight, that's great. If you can't, don't panic about it. Just do what you can. Okay, and we'll take a look at that sort of stuff a little bit more detail tomorrow. Remember, Other than this, no homework. Okay, please make sure that you're ready for tomorrow's quiz, though, in elastic collisions. Okay.